Hi everyone. The next topic in the series is about the integral as net change. And this is a really important concept to understand as we find the integral. So this idea of an integral comes about from, as you recall, Riemann sums, or dividing up an irregular shape into regular pieces that the area can be computed. You know, these are just rectangles, so you have a width and then you have a height. And we talked about left point Riemann sum, where the height was the left side of the rectangle. A right end Riemann sum is the right side. Notice that the left one on this particular curve, concave up and increasing, is the least amount of area. It underestimates. The right point overestimates, and a midpoint gets a lot closer. You can see that it's not exact, but it gets a lot closer. We could get even closer if we made these rectangles a lot closer together. In fact, we could get extremely close if we used infinitely small rectangles to divide up this place. And this is the idea of an integral, taking the limit of the number of rectangles underneath the curve. So, except we can't do that by hand. I mean, we can't divide up things underneath there. So we developed integral calculus so that we can get exact answers with just a little bit of effort. So this is a really important concept, that when you want to find the cumulative effect of a varying rate of change, integrate it. So in other words, if you have, this is just another one. This shows right here that if you had a constant velocity, then you could find very easily the area under a curve, even if you just divided it up into a small chunk. But this idea of cumulative effects, that you're accumulating the effect, like you're pouring water into something, it's going in at a rate. How fast is it accumulating? There's an oil spill. How fast is it? You know, that's a rate. So we can use the integration, idea of integration, to find it. So how do you set up a function to be integrated? So if I had a graph, something that looked with a curve, right, and I know that this is A and this is B, and I wanted to find how much area it is between that of this function, f of x, then of course we would set up the definite integral that would go from A to B of f of x dx, and that integral would then find the area under the curve. If we were going to use Riemann sum notation, we would say the sum of the area of all the areas underneath here times delta t. So we would take like this length right here, f of x, or f of t, I guess, and then this width here would be delta, the change in t. And so if you, that turns into the area between of f of t dt. So there are three general strategies for modeling with integrals. So the first thing is to actually approximate what you need to find as a Riemann sum. And we remember that area is, you would find it by adding the areas of the rectangles. So you would add area of rectangle. And the area of a rectangle is height times the width of each one, right? The area of each rectangle. And so if you wanted to add up all those areas, that would be the sum of the height, which is f of x, the y coordinate, times delta x, which is all the widths. And then if we took that and found the limit as n approached infinity of the sum of all the heights times the widths, then we would approximate the area under the curve as a definite integral from a to b of f of x dx. And all of this means the same, right? So this would be net accumulation. Right, so the first is to approximate as a Riemann sum. The second is to write the definite integral. And then the third strategy would be to evaluate that numerically or with an antiderivative. So an example would be if we had a car that was moving with an initial velocity of 5 miles per hour, and it accelerates at a rate of t equals 2.4 t, f of t, equals miles per hour per second for 9 seconds. And so we want to know how far is the car going when the 8 seconds are up, and B, how far did the car travel during those 8 seconds. So you can see that in A, we're talking about displacement. And B, we're talking about total distance. So if we wanted to approximate it with a Riemann sum, right, we would have a velocity change which would be equal to the acceleration times the time applied. So acceleration is a rate of change times time. So you would have the acceleration at time t sub k times the change in time, and that would be miles per hour. And then we would have that times the time. So it would be miles per hour per second squared. Right? If we take the sum of all those areas, it would look something like this notation. And so this would be the net change in velocity where between 0 and 8. All right. So what was t sub k? Well, t sub k is going to be any point in the kth subinterval. All right. So that's how you would do it as a Riemann sum, to approximate it as a Riemann sum. So how would we write that as a definite integral? How would we write velocity as a definite integral? Well, we would write this. We want to go from 0 to 8 seconds. And if we're finding velocity, we're going to integrate the acceleration. Okay? So if we fill that in, then, see, that was part 2 that we did before. This is part 1, Riemann sum, definite integral. And then 3 is evaluate numerically. So the net velocity change, is equal to the integral from 0 to 8 of 2.4 t dt, which would get me 1.2 t squared, 2.4 t squared over 2, from 0 to 8. And if we evaluate that, we get 76.8 miles per hour. So A says, how fast is the car going when 8 seconds are up? So initially, we were going 5 miles per hour. We used the definite integral to find the accumulation of acceleration for 8 seconds, which was 76.8 miles per hour. And if you add those together, we were going 81.8 miles per hour. That's how fast. The second question was how far does it travel? All right, so we know that we knew what acceleration. We found that the acceleration was A of t was 2.4 t miles per hour per second squared. Okay, so it had an initial velocity of 5 miles per hour. Okay, so when we go to find the velocity, right, we have to integrate 2.4 t, but we also have to add to that, this would be from 0 to t dt, we would have to add to that the initial velocity that we were given in the beginning, all right? So all of that is going to equal velocity. So when we integrate that from 0 to 8, or when we figure what this is, we would have 5 plus 1.2 t squared miles per hour. So that this is the velocity. So when we want to find total distance, remember that the total distance is the absolute value of velocity, right, dt. So if we substitute everything for that, if we have 0 to 8 of the absolute value 5 plus 1.2 t squared dt, we're going to end up with 244.8 miles per hour per second. And so this miles per hour we're going to need to convert. And that'll be on the next screen. Okay, so we need to convert. So we have 244.8 miles per hour per second by second. Okay. So I have per second, I've got that right, and then times 1 hour, this is my conversion, 1 hour is 3,600 seconds. All right, so the hour cancels with the hour, the second cancels with the second, and I end up with miles. So if you do 244.8 divided by 3,600, you get 0.068 miles. So therefore, the car traveled 0.068 miles during 8 seconds. I really have nice handwriting, you can't tell here, of acceleration. So here's one final example about the consumption over time. So once again, using the definite integral to model the consumption rate or model a rate of change over time. And so from 1970 to 1980, the consumption rate of potatoes, and it could be anything, it just happens to be potatoes this time. It could be any date, can be anything, you can fit anything in here. But here it is modeled by this equation. Millions of bushels per year. T represents the number of years since 1970. How many bushels were consumed from the beginning of 1972 to the end of 1973? To the end of, okay? So let's talk about time. Well, time is going to be somewhere between, 1972 is 2 years past, end of 73 would be to 4, right? Not the end of 4, but the beginning of 4. So the cumulative effect of a consumption rate, right, would look like this, from 2 to 4 of this function, c of t, dt. So if you replace it with the actual function, and you've got 2.2 plus 1.1 to the t dt, that would be millions of bushels of potatoes, right? Put it in your calculator, and you would get 7.066 million bushels consumed between the beginning of 1972 and the end of 1973. All right, so we're going to do some more of these. A lot of this is review, but it's also adding the concept to some of the techniques that we've used. And so we'll finish up and work on this, and then we'll begin working in more detail with integrals. So I'll see you in class.